Maxim Altyntsev, Siberian State University, or Geosystemic Technologies. He will speak about forest space image decoding using the structural statistical approach.
Good afternoon. I'm going to cover the yet uncovered section. I will talk about image decoding or interpretation. The toughest part is identifying varieties of trees or forest valuation characteristics. We don't have a single modality that would be good at forest classification. It's something I've been doing for many years now, just to distinguish different elements, different objects on the image. Interpretation is looking for a vector of attributes that are interrelated with the image's brightness on the map and on the terrain. There are different approaches to classifying images, of course. They can be divided into key groups. One is structural, the other one is spectral. When we talk about spectral properties, we assess brightness of pixels. But when we talk about structural parameters, we assess linkages between neighboring pixels. So the purpose of the structural approach is to analyze neighboring pixels' brightness levels. And this analysis is done on a grouping basis. Depending on the types, different approaches can apply, parametrical or non-parametrical. I will elaborate on the essence of the non-parametric approach. Here we analyze functions that are distributed differently from normal. If it's closer to normal, it's parametric approach. If it's not close, it's non-parametric. Our institute has been handling this issue for many years already. The main idea took shape 5 years ago, and since then we've made significant headway. The essence is, you take a map, let's say tree variety map of a forest, and now we need to come up with reference standards, references. References must be of pretty big size. It could be plots of land, let's say 3 hectares or 5 hectares, and then you build a function in the form of probability density, which will show you a probability of finding a pixel of a certain size. And the cumulative distribution function is derivative of distribution. And values are positioned between 0 to 1. So it's important to collect an optimum criterion. Application of decision rules. It was suggested to use as a decision rule the correlation factor, or to use minimum distance when we analyze distribution functions. Here we apply Pearson coefficient, and in the second minimum distance approach. The entire function needs to be divided into 10 intervals. and then we measure distance from one function to another on a scale of 1 to 10. 1 to 10 range has been employed experimentally because we believe it delivers the best result. And the estimation is done on each spectral band separately, or we can measure cumulative distance. In other words, 4D application. 4 bands, we know that there can be more channels, like 6. If it's 6 channels, then it'll be a 6D function. The testing of the results was done based on 4-band images. This is Iconus space image, 10 years old, and we used the thematic map for species composition of forest. Birch, aspen, alder, pine. I mean, tree varieties were scarce. This is near Bertsk city, on the border of Pskov water reservoir. First, we needed to collect reference samples. Here you can see 5 of those that were used for decoding later, represented in real scale. The largest was the coniferous tree section in the middle, pine trees, covering 5 to 6 hectares. And the smallest one was aspen tree section. The sample size was based on data availability and potential size of each reference area. Plus we had water and ground territories. Then we generated functions using all channels. RGB, of course, this is an example of the red channel. So first we generated reference samples, and then we used some test strips. We knew for a fact where this or that section belonged to, so then we could proceed to decode it. In our case, this is pine trees area. So this sample is closest to the reference sample of pine trees, with the correlation factor at 0.9, which is closest to 1. This is an example of generating cumulative distribution function in all spectral bands at once with the test sample. 0 to 1 range, and the distances are also shown on this slide, from test sample to each of the reference samples. In the red band, we can see that there is a match with 0 value, but not all the channels have been properly decoded. In some of the channels, decoding reliability was higher. Also, we had some false classifications. So the object was to figure out which function is the best for particular decoding. These are results of decoding. It shows how many reference samples were selected and the number of detected ones. By decoding particular species of deciduous trees, like aspen and birch trees, the results originally were pretty poor. It was a failure. So what we did was to assume that birch and aspen trees would be decoded as one group, let's say deciduous. And in this case, the green channel delivered 100% in terms of distribution. If we take 4D cumulative distribution, 17 out of 18 have been properly decoded. As you can see, it's much better than when taking it separately, tree variety by tree variety. And this is the same table, but in percentages, in ratios. So 4D decoding delivered the best results in a cumulative distribution function with 85%, which is not the most desired result, of course. What we did next was to choose several reference samples and combined into one. So the function was generated built on several references. For example, this is the example of generating probability density functions for aspen trees, with all the resulting brightness differences. The number of sections was 5 for each tree species, and then for water and for the ground. As for the ground, we didn't have true results, so they were false, even though we expected a different outcome, considering that it's spectral imaging. Let's see what happened with new types of reference samples. Again, this is the cumulative distribution function graphs based on several or combined reference samples. So it becomes a well-curved graph for different bands. And these are results of decoding using the common functions. For some species, the results have improved. Birch, aspen are okay, but for aspen, the reliability rate is not particularly impressive. And deciduous trees in general have been decoded pretty well. 4D decoding is reaching a maximum. And finally, the ground had good results when analyzed as a common function. In particular, that applies to infrared channel, 5 out of 5. Again, 4D density distribution delivered the best results. It's 8% higher than when using separate functions. So it's best to form an averaged reference. These are the same graphs that I showed earlier. You can compare them with a set of images that I showed before. The test sample is the same. It's a match. And the cumulative distribution function, I showed it already. So, the conclusions. The structural-statistical approach helps decoding space images better in many cases by using spectral approach. And you need to rely on heavy statistics and reference samples. Individually, aspen and pine trees have been recognized with 80 to 90% reliability. But what we need to do now is try to potentially use another space image. So we got our work cut out for us to recognize tree varieties individually, because it's still a challenge. That's it. Thank you. Any questions? I have two questions. How come in the common reference samples we had several maximum values? I mean, how come you took different sections with different lighting conditions? Yeah, we assumed that the lighting conditions are the same. Naturally, if we use the different images, they would have different lighting conditions. But we tried to level it out. We cover a larger spectrum with this approach when building those functions. I'm curious, you detect coniferous and deciduous vegetation, but what if you picked a test area on the other side of the water body? I think it would still work. I tested other data, of course. If we take spectral features, things are much worse there. You have to basically generate a function anew. This approach doubles the result. I would recommend that you use multispectral imagery. The more spectra you have, the better chances you stand of detecting tree species individually. Thank you. Other questions?